At the other end of the optical fibers, there's a spectrograph, one of the biggest spectrographs, certainly the biggest spectrograph ever built in Australia, to accommodate these 400 fibers and actually create 400 spectra very efficiently with the minimum loss of light. So very demanding technology, and it's only thanks to the very clever engineers we have here at the observatory that we can have this in the facility running.
That's incredible. I guess, judging by the size and weight of it, not every telescope around the world is going to be able to accommodate such a beast. Is that right?
That's the interesting thing. This is a telescope that's 30 years old. It wasn't designed to have this extra large robot weighing hundreds of kilograms. Plus, in fact, there's also a wide field corrector to focus the light over a wider field. It's like putting a new lens on a camera. This has got 4 very large bits of glass to re-image the telescope onto a bigger field. A lot of extra weight on top of the telescope. If this telescope had been designed today, it would have used advanced engineering and computer design to optimize it to be just as strong as needed to perform its function. Back in the 1960s, when it was designed, they didn't have those computer modeling facilities, so they just built it very strong with lots of big safety margin. That's been a lifesaver because of that big safety margin, we could put an extra several hundred kilograms on top of it and it could still support it. Even so, it does bend when you tip it over, and so there's a lot of very complex computer modeling going on inside there, inside the positioning, to correct for all the flexure and bending of the system.
Right. Okay. So, in terms of the project now, whereabouts are we now? Because I think you now actually finish that project this year and conclude that and look forward to some results, I guess.
That's right. We'll finish it this year. We have an allocation of about 230 nights on the telescope, and this is the final semester of that allocation. So I'm here at the telescope for one of our 15-night observing sessions. Fortunately, my personal shift is only 6 nights, and someone else is going to take over. We have processed the data from the first 3 years of observing, and we have the final 4th year still to go. We won't get the answer to the experiment till we've got the complete 4 years worth of data. So I'd say at least another year and then at least 6 months for processing before we get the answer about dark energy, the answer about picking up this pattern in the distribution of galaxies and being able to answer this question, does the dark energy change over time? But we do have 100,000 galaxies already processed and analyzed, and we're getting some very nice results out right now. And the first one is being able to use them to see how gravity is gradually over time building up larger and larger structures in the universe. In the early universe of Big Bang, everything was spread out very smoothly, and over time, little irregularities in that distribution get bigger and bigger as gravity collects material together to form stars and galaxies and clusters of galaxies and ever increasing structure in the universe. And we can actually see that process happening through this survey already with the 100,000 galaxies, and we've made some measurements which we can compare with some of the theories, and already we're beginning to answer some of the interesting questions. And the first result we've got out, just coming out this year, is that one of these alternatives to dark energy, saying that the law of gravity is wrong, is actually not consistent with the results. So we can already rule out one of those alternative theories, and we're hoping to publish that very soon.
That sounds fantastic. And certainly you allude to the fact that there's been quite some controversy about whether this stuff is just the figment of fertile imaginations from astronomers looking for extra grants, or whether there really is something out there that physicists can go out and measure. So maybe you can actually just give us some brief history of some of the controversies that were out there in recent times.
Lots of interesting questions there. I might just brag a bit and say, apologize if I'm shivering a bit. This dome is specifically air conditioned to stay at the nighttime temperature, so it's time during this interview, but the temperature I'm sitting in is actually what it would be like outside during the night. Anyway, so your question was about the controversies about dark energy, and in answering that, I should also talk about dark matter. We now know through the wonderful results from looking at the distribution of galaxies, the signals from the microwave background that come as radio waves from the very beginning of the universe in the Big Bang, and the supernova experiments, we've put together a very consistent picture where the universe is built up of matter that experiences gravity, and then this new stuff we call dark energy. In the matter, which feels gravity, there's two types of matter. There's ordinary stuff that telescopes and planets and stars and people are made of. We call that baryonic matter. It's made up of atoms, like we're very familiar with. Since 1935 maybe, we've known that there's something that's more than just the visible normal matter in the universe. When we look at galaxies that rotate, we can estimate how much mass there is from looking at all the stars. And we see very soon that they're rotating too fast for the gravity of the visible material to hold them together. When you look at groups of galaxies that orbit each other, again, they're moving too fast to stick together, just relying on the gravity from what we see. And so since the 1930s, there's been this idea that there is extra matter providing extra gravity that we can't see, that we call dark matter. That's been very well established for many decades now, with lots of different experiments using obviously the rotation of galaxies, movements of galaxies, how light is bent by the gravity of the extra mass, saying that for every bit of normal matter we see, there's something like 8, almost 10 times as much total matter, but up to 80% of it is actually dark, we can't see it. And it's not just dark that we can't see it, it cannot even be made of normal material like ourselves, of normal atoms, it's something else. So already there's a large bit of the universe that's not visible, it's some other kind of material, but it does have gravity, and we can very clearly see the effects of its gravity. It's definitely there. We just don't know what it is yet.
Okay.
Over the last 3 decades, we've been eliminating various options for what it is. That's the dark matter, about 8 times the normal matter. The new results on the expanding universe getting faster show us that there's a whole lot of extra stuff in the universe making it expand faster that's actually a lot more than the normal matter and the dark matter. We're now looking at a universe which is only 5% normal matter, like you and me and our planets and telescopes. It's about 25% dark matter, which we can't tell you what it is, but we know it's there very clearly. And then 70% dark energy pushing things apart. So the normal material in the universe is now only a tiny fraction of the universe. Do you believe me? Would you believe me?
I'm having some trouble here. It's very controversial. Some people say that maybe this dark stuff is all something to do with the Higgs boson particle, or God's particle, or God works in mysterious ways out there and is actually just antagonizing astronomers and astrophysicists. But I'm sure that's not right.
So there's a number of alternatives. You've got to allow the fact that we're missing. There are other explanations. However, as I said earlier, the dark energy does solve that very embarrassing problem of the universe before was not old enough to contain the star cluster, so that fits in very nicely. So that's one indication we're on the right track. There are alternative explanations. A very interesting one is that we're not actually seeing this acceleration because of dark energy pushing things apart, but we just happen to be sitting in a region in the universe that's has less material in it than average, and therefore the surrounding universe is actually denser than where we are, causing stuff to move outwards due to the gravity beyond where we sit.